So to this point, we've talked about matter, and we might be wondering, well, what is matter made out of? And early scientists also wondered that and explored it. So the first people to kind of think about matter and what it was made out of are the Greek philosophers. And so some Greek philosophers, like Democritus, believed that there was a small particle, which he called atomus, which means uncuttable. It's where we get the word atom from, that made up all of nature. Now, experiments in the 18th and 19th century led to an organized atomic theory by John Dalton. And this fine fellow here is John Dalton. And this had several points. The first thing that he said is, hey, look, all matter consists of tiny particles called atoms. And then he said, hey, look, an atom cannot be created or destroyed or converted to any other type of atom. He said that atoms of a particular element have identical properties and atoms of different elements have different properties. He said that atoms of different elements combine in whole number ratios to produce compounds. Right? So a stable combination of atoms. And then he said chemical change involves joining, separating, or rearranging atoms. Now, 1, 4, 5, and 6 are still regarded as true. When we look at number 2 here, an atom can't be created or destroyed or converted to any other type of atom. We now know through radioactive experiments that that's not the case, so that he just didn't know about radiation at the time. And so in radiation, you can have an atom that's turned into another atom. And then this with the identical properties here, atoms, you can have isotopes of atoms, and so that's why this is no longer considered to be regarded as true. So that's kind of the basis for how we started thinking about atomic theory. Now, a really big thing to think about here is that electricity wasn't widespread. So for a really long time after this was the early 1800s, then we didn't have a lot of discoveries that came along until electricity came along. Now, Eugene Goldstein in 1886 was a German physicist. He was the first to discover that a positively charged particle formed when electrons were removed from the gas particles in a cathode ray tube. This is an example of a cathode ray tube. It's just a tube that has electricity running through it. There is an anode and there is a cathode. He was very interested in electrical discharges in moderate to high vacuum. So there's a vacuum that is here as well. And his work suggested there was the presence of a proton, which was a positively charged particle, and that was later discovered by Ernest Rutherford. They have backtracked to say that he's probably the first one who really observed those positively charged particles. Now, J.J. Thomson discovered electrons in 1897, also looking at cathode ray tubes. So his experiment identified a negatively charged particle that was emitted from an electrode in the cathode ray tube. So basically what happened is when electricity was passed through the evacuated glass tube, a stream of particles was emitted from the cathode and traveled to the anode. Now, this is a magnet, and the important part here is the particles were consistently deflected under the influence of electrical or magnetic fields. So you would hold up a magnet, and those particles were attracted to the magnet. You would flip the magnet around, and the particles were repelled by the magnet. So that indicated that those were charged particles. So we're going to put some words to this. So J.J. Thomson, which you can see right there, he discovered electrons in 1897, and the beam from the cathode ray tube was deflected toward the positively charged plate. Right? And so from this, he concluded that atoms contained negatively charged particles, right, that we call electrons. Right? Now, Thomson measured the charge to mass ratio of the electron, and he determined that to be 1.76 times 10 to the 8th coulombs, which is a measurement of charge per gram. Okay, so this was the charge to mass ratio. Okay, you don't need to memorize that, but it is important to realize that at this stage we had a charge to mass ratio. So if you could figure out the mass of an electron, you could figure out the charge of an electron, or if you could figure out the charge of an electron, you could then figure out the mass of an electron. So another fellow came along, his name was Robert Millikan, and he really advanced Thomson's work by determining the charge on the electron through an oil drop experiment. So oil drops, this was his experimental apparatus here, okay, and he had oil drops here that were created within a atomizer, and they fell through a pinhole into a lower chamber here. Then the mass of the droplets were calculated by measuring their rate of descent due to gravitational forces. In this lower chamber, he also had X-rays that would ionize the gas molecules by removing the electrons, and those were picked up by the oil droplets. He could adjust the electric fields between the two plates, so we've got a plate here and a plate here, and calculate that mass to charge ratio of the droplets. Since that the mass of the droplets were already known, then he could figure out the charge of the droplets, which were the charge on the electron. And then once that electron charge was known, the mass of the electron was then calculated. So he figured out the charge of an electron, and from this he could figure out the mass of an electron here. I'm going to put up a video for you to see this. It's a demonstration. It's probably a 2-minute video, because I used a lot of words there, but for you to see it is a lot better. So we know they're electrons. We now know the mass of an electron and the charge of an electron. So J.J. Thomson discovered those electrons in 1897 by using a cathode ray tube, but he was not sure where the electrons fit with the structure of the atoms. And so when he was coming up with a model for the atoms, what he came up with was the plum pudding model, where he said, hey, look, we've got electrons and they're going to be distributed throughout a diffuse, positively charged sphere. Now, what does that mean? So plum pudding, if you've never had plum pudding, this is what plum pudding is. It is a cake, and then it's got fruit that's embedded in it. You might think of bread pudding if you've ever been to Louisiana. It's very similar to that. And this was a big dessert at the time. So what he was saying is, hey, look, the atom itself has really diffuse positive charge, and that's like the cake part. And then the electrons are embedded in there like the raisins or the fruit of the plum pudding, or the plums of the plum pudding. And so this is what he proposed was the structure of the atom. Now, around this same time, radioactivity was discovered, because, well, radioactivity was discovered, and that did cause the plum pudding model to be readjusted. Okay, so let's talk about radioactivity for just a second. Henry Becquerel was a French physicist in about 1896, and he was investigating radiation that was coming out from a material called pitchblende, which was a uranium ore. And he determined that these were charged particles. So Henry Becquerel came along and said, some materials produce invisible radiation consisting of charged particles. And I have an example of pitchblende right there that they were studying. Now, he worked closely with Marie and Pierre Curie. They also showed radiation consisted of small particles. Right? So what is radioactivity? When we talk about this, this is just the spontaneous emission of high energy radiation and particles. And there were two particles in particular. There were beta particles, which have a symbol that looks like this. They are high energy electrons, and I'm going to abbreviate electrons like that. And then we also had alpha particles, which they look like this, or they look like this, right? They have a positive 2 charge, and they have the same mass as a helium nucleus. So, So we've discovered radioactivity, right? And so we can study these particles. And a guy named Ernest Rutherford, who was a physicist from New Zealand, wanted to validate the plum pudding model. And so what he did is he took those radioactive particles, so he took an alpha emitter here, and he bombarded a thin gold foil target with the alpha particles. And if the plum pudding model was true, right, then what he'd expect is that those particles would pass right through, because the positive charge would be so diffuse, it would not deflect them very much, if at all. It might deflect a little bit if they ran into an electron, but this is what you would expect, right? Now, what actually happened is he got wide deflections. So when he was measuring this, the particles were bouncing back. They were coming straight back. Some of them did pass through, but he got a lot of big deflections there. So what he then concluded is the plum pudding model was not correct. Instead, what he proposed was a dense region of positive charge, which we now call the nucleus. So based on his gold foil experiment, he proposed an area in the atom of dense positive charge, which we now call the nucleus. Okay. So in science, as we go along and we learn more things, we go back and we reevaluate our models. And so Thomson worked with what he had at the time. Radioactivity was not discovered when he was doing his initial research. And we discovered it, and then this experiment showed something different, and science reevaluated their model. Now, so we've talked about how the electron was discovered. We've talked about how the proton and that dense nucleus was discovered. But let's talk about the neutron. So this fine fellow is James Chadwick. He was an English physicist. And what he did is he bombarded a thin sheet of beryllium with alpha particles. So this is his polonium source. There are his alpha particles, and he's bombarded that thin sheet. Now, when he did that, a very high energy radiation was emitted by the metal that was not deflected by either electric or magnetic fields. And so for us, that meant that there was no charge, right? If it's not being deflected, that means there is no charge, okay? The radiation consisted of a third type of subatomic particle, which Chadwick named neutrons because they were electrically neutral particles. And they had a mass that was slightly greater than that of protons. So that's how we discovered neutrons. So where are we now? So now we're at the nuclear atom. This is the atom that you're probably most familiar with. It's an atom with a nucleus, right? So a positively charged center of the atom that contains nearly all the atom's mass. It consists of two types of particles. It consists of protons, which are positively charged, and it consists of neutrons, which have no charge or are neutral. And those are the two particles in the nucleus. And then we have electrons that are not in the nucleus. And those are negatively charged. And you can see on the image here, right, if this is a gold atom, then the nucleus is here, and then all the electrons can be within the space around the nucleus. And the nucleus itself consists of protons and neutrons. So, in summary, here is our current working of the atom. We have electrons. They're represented with an E minus. We say their charge is -1. And then we see that the mass is much, much smaller than either protons or neutrons. Protons, this is the symbol we use there. We say they have a +1 charge, and we can see their mass there in atomic mass units. And then neutrons have about that same mass, and those are neutrally charged. So do not memorize any of these masses. You do need to know the charges. What you need to know about the mass of protons and neutrons is they're about the same, and then electrons are much, much smaller.